good to see all of you. You see a quote up there by Niels Bohr, one of the founding figures of quantum mechanics. Anyone who thinks they can talk about quantum mechanics without getting dizzy hasn't yet understood the first word of it. Now, why would that be? What did Niels Bohr mean by that? Well, basically he meant that we all have a good intuition for classical physics, right? And by that I mean, if I was to take any little object, right, give it a catch, nice, did a one-handed catch right there, throw this a little bit further back, and we go 2 for 2. No, we're 1 for 2. They're still back in the dark age. Here we go. You have that one over there? Good. Right now, each one of the people who caught, so that would be the 2 of you over here, is a really evolved human being. No, you see, when we were out there in the savannah trying to survive, right, we needed certain skills. We needed to be able to know where to throw a spear, how to throw a rock to get the next meal. We needed to dodge some animal that was running toward us, and therefore we learned the basic physics of the everyday macroscopic so-called classical world. We learned that intuitively. And that's why when I throw an object, you don't have to go through some elaborate calculation to figure out the trajectory of that stuffed animal. You just put out your hand and catch it, right? It's built into our being. But that's not the case when we go beyond the world of the everyday. If we explore the world, say, of the very small, which is what we're going to focus on here tonight, we don't have experience in that domain. We don't have intuition in that domain. And in fact, were it the case that any of our distant brethren way in the past, if they did have some quantum mechanical knowledge, and they sat down to think about electrons and probability waves and wave functions and things of that sort, they got eaten. Their genes didn't propagate, right? And therefore, we have to use the power of mathematics and experiment and observation to peer deeper into the true nature of reality when things are beyond our direct sensory experience. And that's what quantum mechanics is all about. It's trying to describe what happens in the microworld in a way that's both accurate and revealing. And the thing to bear in mind is, even though our focus here tonight will really, in some sense, be in the micro world, the world of particles, we are all collections of particles. So any weirdness that we find down there in the micro world, in some sense, it has an impact even in the macro world, and maybe suppressed, as we'll discuss. But it's not like there's a sharp divide between the small and the big. We are big beings made of a lot of small things, so any weirdness about the small stuff really does apply to us as well. And in this journey into the micro world, the world of quantum mechanics, we have some of the world-leading experts to help us along to figure things out, and let me now bring them on stage. Joining us tonight is a professor of philosophy at the University of Southern California, who spent 22 years at the University of Oxford as a student, researcher, and faculty member. He is the author of a book on the ever interpretation of quantum mechanics titled The Emergent Multiverse. Please welcome David Wallace.
Thank you.
Also joining us tonight is a professor of chemistry at the University of California, Berkeley, co-director of the Berkeley Quantum Information and Computation Center, and faculty scientist at Lawrence Berkeley National Laboratory. She's a fellow of the American Physical Society and a recipient of awards from the Bergman, Sloan, and Alexander von Humboldt Foundations. Please welcome K. Birgitta Whaley. Our third participant is a professor of physics at the University of British Columbia, a Simons investigator and a member of the Simons Foundation IT from Qubit Collaboration. He was a Canada Research Chair and a Sloan Foundation Fellow, and was awarded the Canadian CAP-CRM Medal to Theoretical Mathematical Physics in 2014. Please welcome Mark van Raamsdonk. Our final participant is a professor of theoretical physics at Utrecht University in the Netherlands and winner of the 1999 Nobel Prize in Physics for work in quantum field theory that laid the foundations for the standard model of particle physics, one of the greatest minds of our era. Please welcome Gerard at Hooft. All right, so the subject is quantum mechanics, and part of the evening will involve some challenge to the conventional thinking about quantum mechanics. And so before we get into the details, I thought I would just sort of take your temperature, get a sense of where you stand on quantum mechanics. Is it, in your mind, a done deal? It's finished. We completely understand it. Is it a provisional theory? Is it something which 100 years from now we're going to look back on with a quaint smile? How do they think that that's how things work? So David, your view.
Well, I don't think we fully understand it yet. I think it has a lot of depths left to plumb. And who knows, it might turn out to be replaced. But right at the minute, I think we don't have either empirical or theoretical reason to think that anything will take its place.
Good. Birgitta.
I think it's here to stay. There may be modifications.
Here to stay, you said.
Yes. Here to stay. There may be extensions and modifications. There may be something more complete, but this will still be part of it.
Okay. Mark.
Yeah, so there's a frontier in quantum mechanics that I work in, and this is the frontier. It's like the wild west of theoretical physics, where we're trying to combine quantum mechanics and gravity, and we need to do that to understand black holes and hopefully eventually understand the Big Bang. And there's a lot to do, and we don't know if we're going to have to modify quantum mechanics or it'll all be the same quantum mechanics. But,
all the way down,
yeah.
Right. Now, Gerard, you have unusual views.
Well, yes, I could spend the rest of the evening explaining them.
Yes.
But to my mind, quantum mechanics is a tool, a very important mathematical tool to calculate what happens if you have some underlying equations and to telling us how particles and other small things behave. We know the answer to that question. The answer is quantum mechanics, but we don't know the question. That's still something that you have to figure out.
Good. So it's sort of a Jeopardy issue, if you know the American reference. All right. So just a quick overview. We're going to start with some of the basics of quantum mechanics, just to sort of make sure that all of us are more or less on the same page. We'll then turn to a section on something called the quantum measurement problem, something weird, quantum entanglement, as in the title of the program. We'll then turn to issues of black holes, space-time, and quantum computation, which will take us right through to the end. All right, so just to get to the basics of quantum mechanics, the story, of course, began more or less in the way that I started. You know, we understood the world using classical physics in the early days, way back to the 1600s. And then something happened in the early part of the 20th century where people like, we started with Newton, of course, then we move on to people like Max Planck, Albert Einstein. What drove the initial move into quantum physics? David?
I think it was really just pushing really hard at classical mechanics as it went down into the scale of atoms and the structure of atoms, and just finding that structure snapped and broke. That trying to use classical mechanics to understand how hot things got or how electrons went round atoms without collapsing into the nucleus, in all those places we had a series of hints that something was amiss in our classical physics.
Yes.
And it took, I guess, most of 30 years for those hints to coalesce into a coherent theory. But that coherent theory then became not really just a single physical theory, but a language for writing physical theories, be it theories of particles or fields, maybe someday even gravity. And that language was more or less sort of solid by, I guess, about 1930.
Yep. And it's actually quite remarkable that it only took that number of years to develop a radically new way of thinking about things. And Richard Feynman, who is, of course, a hero of all of us, also known to the public, famously said that there was one experiment. We could go through the whole history of everything that you described with the ultraviolet catastrophe and photoelectric effect and all these beautiful experiments, but the double slit experiment, luckily for us in having a relatively brief conversation, allows us to get to the heart of this new idea, where it came from. This actually is the paper on, in some sense, the double slit experiment, the first version, Davison and Germer. And I'll draw your attention to one thing. You see the word accident? And this is just a footnote, but in the old days, people would actually describe the blind alleys that they went down. in a scientific paper, but as science progressed, we were kind of taught, no, don't ever say what went wrong, only talk about what went right. But here's an old paper, and indeed this experiment emerged from an accident in the laboratory at Bell Labs. They were doing a version of this experiment, they turned the intensity up too high, some glass tube shattered, and when they redid the experiment, unwittingly, they had changed the experiment to something that was actually far more interesting than the experiment that they were initially carrying out. So just to talk about what this experiment is in modern language. So David, again, what's the basic idea of the double slit experiment?
So you take a source of, well, of particles of any kind, but let it be light, for instance. You shine that light as a narrow beam on a screen. It has 2 gaps in it. And you look at the pattern of light behind the 2 gaps in the screen. Two slits,
Yeah,
exactly,
yeah,
yeah. So the slits are just literally gaps in a black sheet of paper, in principle. Yep. The light's going through. If light is a particle, you'd expect one sort of result on the far side of the screen. If light is a wave, you might expect something different, as the light coming through one part of the slit interferes with the light going through the other part of the slit. And the weird thing about the quantum 2-slit experiment is that it seems in various ways to be doing both of those things at the same time.
Good. So, Birgitta, if you can just take us through a particle experiment to build up our intuition. So let's say we carried out the experiment that David described, but we don't start with photons or electrons, we start with bullets or something. So I think we have a little animation that you could take us through. So what would we expect to happen in this experiment?
Well, so you have the source of the pellets here in front, and it's spitting out the pellets, and some of them go through the holes, and the ones that go through the hole, they sort of travel rectilinear, straight ahead, as we might expect from our classical intuition, and we get 2 bands at the back, indicating the pellets that went through the right slit on the right, and the left band is the pellets that went through the left slit.
Now, if I was, that's completely intuitive, right? So this is the stuff that our forebears would have known even on the savannah, right? Now, if we took the size of the pellets and we dial them down to a very small size, before going to your quantum intuition that you have, what would you expect naively to happen if you simply dial down the size? Would you expect there to be anything different if you were... this is a leading question, by the way. So just follow me here. The answer is, would you expect anything different? Would you expect anything different? No, not at all. Good. So
Naively not.
Naively not, exactly right. So here's what you would naively expect would happen. Again, you've got the particles going through the 2 slits. So Mark, tell us what actually does happen. Not that I don't think Birgitta could, just to give us all a little airtime.
So of course it's kind of wild. The place where you would least expect to see something on that screen is exactly behind that big barrier that's in the middle.
Yep.
And somehow, when you actually do the experiment, you see that actually that's where most of the particles end up. So it's almost exactly the opposite. And then you get this weird pattern with other bands going out. And so you initially would stare at it and shake your head and wonder what you'd actually
So we'll analyze what that means in just a moment. But we often, I don't know, probably almost everyone in this audience has seen a still image or an animation like this in the discussion of quantum mechanics. And I thought it would be kind of nice to show you that this actually happens. It's not just animation that an artist does. So we're going to actually do the double slit experiment for real right now. And to do that, I'm going to invite a friend of mine from Princeton University, Omelan. Can you wheel out, if you would, the double slit experiment? All right, so what we have here is a laser on this far side. So this is our source. So actually we're doing this in some sense opposite to the orientation that we saw in the animation. And we're going to fire this laser, which is photons in essence. And the photons are going to go through a barrier that has 2 openings in it. It's harder to see that, of course, mechanically. But trust me, there's a barrier with 2 openings. And we're going to take a look at the data that falls on a detector screen, which in the modern age is a more complicated and somewhat finicky piece of equipment. So we're all sitting here on spilkas. If you speak any Yiddish, you know exactly what I'm talking about right there. But hopefully this will work out. So Oman, why don't we just actually see ambient noise? Can we see a little bit of that first? So can we switch over to the input to the screen? All right, so this is the output from that device. And now if we actually turn on the laser and allow us to collect all of the photons that land, there they're building up. And there you see what actually happens. So this is a result of this very device here. And you see it. We have you can see on the very far left, we see some of the photons are landing. Then we get a dark region in between, then a bright, a dark, a bright, a dark, a bright, a dark, and a bright, and a dark, even though this device over here really is a barrier that has only 2 slits in it. So the animation that we showed you actually does hold true in real experiments, and that then forces us to come to grips with it, to try to understand what in the heck is actually going on. So thank you, Oman. So there we have it. We have this situation in which we expected to get 2 bands and we got more. What does that tell us? Where do we go from there?
There's an existing bit of mathematics that comes up with exactly that same pattern, but it has nothing to do with particles. It's the mathematics that you use to describe waves, water waves, or other kinds of waves.
Yeah, so can we see the animation that has a single? So this is a warm-up to the problem where we have water going through a single opening. And just tell us what we see happening here.
That's right. So you've got sort of a water wave, a wave front coming along, and then just that slit acts as a bit of a source for this rippling wave going out in a circular pattern. And you see it's most wavy at the place behind the slit, so the wall. I think that's indicated by the brightness there.
Yep. And then if we go on to a more relevant version for the actual double slit experiment.
Yeah. So now we've got that same wavefront, but now there's 2 slits, and it's like there's 2 different sources of waves. Like if you threw 2 different pebbles in the pond at the same time, and then what happens is that you're both creating waviness, but some places on the screen, the wave from one is doing this, and the wave from the other is doing this, and they kind of cancel out. But right there in the middle, what's happening is that the wave from the one slit is going up right when the wave from the other slit is going up, and then they do this, and you get a big wave, and that's the bright part. But if you work out the mathematics, then the places that have the big waves are exactly these bright ones, and that's just like we saw in the double slit for the particles.
Right. So as Gerard was saying, as Mark is saying, we now have a strange confluence of 2 things. The data that comes out of the double slit experiment when done with particles, and something that seems to have nothing to do with it, where we just have waves going through a barrier with 2 openings. So the conclusion then is that there's some weird connection between particles and waves. That's where that connection comes from. And let's push that further.
Yeah.
So,
I mean, let's just drive home how weird it should be that there is any kind of connection here. So imagine I do the 2-slit experiment. I cover up one of the slits. The effect completely goes away. I get a bit of spreading out of the particles, but I don't get that interference. I don't get those bands.
much as we saw with water going through a single opening.
Exactly. Much as you see with water going through the single slit, and much as you see as your classical intuition about particles. If I cover up the other slit, exactly the same result. It's only if I have both slits open at the same time the effect happens. So it seems to be for all the world as if somehow something's going through the first slit and something else is going through the other slit, and between them they're interacting to create this strange effect. And that's why it matters so much that I can do this experiment with 1 particle at a time. If this was just a mass of light going through, no surprise that some light's going through the left slit, some light's going through the right slit, the left-hand light, the right-hand light interferes. But I can set this stuff up so only 1 photon goes through every hour and a half. I still see the effect. It doesn't go down in the slightest.
Yeah, can we see that? I think we have that.
And then you might be thinking, well, maybe each individual particle breaks in half, and half the particle goes through one slit and half the particle goes through the other slit. But again, then you'd think you could look. Then you'd think you'd be seeing half-strength detections.
Yep.
But that's not what you see. Whenever you look, each time you send the particle through, if you look where it is, you see the particle in one place only. So trying to reconcile those 2 accounts of what's going on makes your mind hurt.
Yep. Exactly. So we're forced into, as David's saying, not just thinking that a large collection of particles behaves like a wave, which maybe wouldn't be that surprising because water waves are made of H2O molecules, particles, and therefore they're kind of wavy. But each individual particle somehow has a wave-like quality. And historically, people struggle to figure out what kind of wave, what is it made of, and what does it represent if you have a wave associated with a particle. A wave is spread out of particles at a point. And it was Max Born in the 1920s who came up with the strange idea of what these waves are. So, Birgitta, what are these waves telling us about?
Well, the waves are, what we see is the probability, which is in the square of the wave, or square modulus of the wave. But
so here's a wave behind you. So you said probability.
Yes.
In essence,
so this is an amplitude. This is an amplitude which will give us a probability. But if we take this amplitude and look anywhere here with some measuring device, we will find with some distinct probability, after measuring many times, we'll find that there's a definite probability of the particle being there, just as in the double slit. After sending many particles through, we found with a certain probability they would all appear on the left. Or all on the right.
So in some sense, vaguely, where the wave is big, there's a high likelihood you're going to find the particle. Where the wave is near zero, there's a very small probability that you're going to find the particle.
But you can't guarantee it. So any one particle could be in a place where the wave is very, very small.
Now these are all just pictures. In the 1920s, physicists were able to make this precise. So Schrödinger wrote down an equation, and I think we can show you what the equation looks like. Obviously, you don't need to know the math to follow anything that we're talking about here. But, Gerard, you wanted to emphasize that there is math behind this because your experience has been that many people miss that point, so feel free to emphasize.
Absolutely. Quantum mechanics, when we talk about it, there's a temptation to keep the discussion very fuzzy. And so I get very many letters by people who have their own ideas about what quantum mechanics is, and they are very good in reproducing fuzzy arguments, but they come without the equations, or the equations are equally fuzzy and meaningless. Whereas the beauty of quantum mechanics is the fundamental mathematical coherence of these equations. You can prove that if this equation describes probabilities exactly as you said before, then actually the equations handle probabilities exactly the way probabilities are supposed to be handled. Except, of course, when two waves reinforce each other, the probabilities become 4 times as big rather than twice as big. But on other spots, the waves annihilate the probabilities, and so the probabilities become 0 where the waves are vanishing. So, but all this hangs together in a fantastically beautiful mathematical manner.
Now, math is one thing, experiment is another. So how would you test a theory that only gives rise to probabilities of one outcome or another? How would you go about trying to determine if it's right or it's wrong?
Yeah, so I mean, it's like if you gave me a coin and you said, this is a probabilistic thing. You flip it, it's going to be heads half the time and tails half the time. And I want to check that. I don't trust you for, I don't know why that would be, but
don't worry, I'm not insulted.
So I just flip the coin, 100,000 times or whatever.
You have a lot of patience to test these things.
The more sure I want to be, the more I flip it. So maybe I do it 10 times. I get 4 and 6, and I'm maybe I'll flip it 100 times, and then I get 48 heads and 52 tails. So I can basically just repeat the experiment a whole bunch of times. And if I have a very precise prediction from those quantum mechanics equations to tell me exactly how often I should expect to get one result versus another.
So I think we can give a little schematic. What are we seeing?
Have a look. Right. So we're doing, there's our wave that's describing the state of the particle, the thing without a definite location. But now we're setting that up a whole bunch of times and measuring where the particle is each time. And these X's are showing the results of our measurement.
That's like flipping your coin and getting ahead or getting
So there's all these possible locations. And what we see is that after a while, the pattern of how often I get one place versus another place, it's matching up to that expectation given by the blue curve, by this wave.
That's right. So we can't predict the outcome of any given run of the experiment, but over time, building up the statistics, we believe the theory if they align with the probability profile given by this wave, whose equation we showed you, and that is what works out the shape of the wave in any given situation. And just to bring this full circle, if we look at the double slit experiment in this wave-like language, now think of the electron or the photon as a wave. It goes through, it interferes like water waves going through the two openings, and therefore you have an interference pattern on the screen which is telling you where it's bright, it's very likely that you'll find the particles. Where it's dark, it's unlikely. Where it's black, there's zero chance of finding the particle there. And therefore, you run this experiment with a lot of particles, and they're going to primarily land in the bright regions. They're going to land somewhat in the grayer regions, and they're not going to land at all in the black regions. And indeed, that's exactly what we showed in the experiment that we ran with the double slit just a moment ago. And that's why we believe these ideas. So that's, in some sense, really the basics of quantum mechanics. Classical physics, particle motion is the intuitive one described by trajectories. In quantum physics, the particle motion is somewhat fuzzier. It's got this probabilistic wave-like character. And the curious thing about a wave, sort of a wave of probability, if the wave is spread out, it means there's a chance the particle's here, a chance that it's here, a chance that it's here, and therefore the wave embraces a whole distinct collection of possibilities all at once. That, in some sense, is really the weirdness of quantum mechanics. So that's the basic structure. And now we're going to move on to our next chapter where we're going to dig a little bit deeper. We'll talk about measurement and also entanglement.
And it's a dead heat. They're checking the electron microscope, and the winner is number 3 in a quantum finish.
No fair! You change the outcome by measuring it.
All right.
Now, either we have a very sophisticated audience or you just love Futurama. I'm not sure which. But this is part of the issue that we now want to turn to, which is if you have a quantum setup, how do you move from this probabilistic mathematics, saying that the electron, say, could be here or here or here with different probabilities, to the definite reality that Mark was describing. When you actually do an experiment, you find the electron here or here or here. You never find anything, a mixture of results. So we want to talk about how we navigate going from the fuzzy probabilistic mathematical description to the single definite reality of everyday experience. And this is something that many physicists have contributed to over the years. Again, Niels Bohr, we had a quote from him early on, and he's certainly viewed as really one of the founding pioneers of the subject. But let's now try to go a little bit further with our understanding of going from the math to reality. And we're going to follow in for this part of the program, really in Niels Bohr's footsteps in something called the Copenhagen approach to quantum physics. So, David, can you just begin to take us through what was the ideas of collapse of the wave function in technical language? What are those ideas all about?
So look at it this way. I've got my probability wave, which is sort of humped, let's say just for one particle. It's humped over here, and it's humped over here. So there's kind of two ways I could think about that. You might say there's an and way and an or way. So I could think of it as saying that the particle is here and the particle is here. Or you could think of it as saying, well, the particle is here or the particle is here. And the problem is I kind of need to use both to make sense of quantum mechanics, or so it seems. So if I try to explain the two-slit experiment, I have to think in the and way to start with. I have to think the particle's going through this slit and it's going through this slit. Because if it's just going through this slit or it's going through this slit, I could close one of the slits and it wouldn't make a lot of difference. But then as soon as I look where the particle is, suddenly the and way of talking stops making sense, because it doesn't seem, we'll come back to this, but it doesn't seem as if I see the particle here and the particle here. It seems as if now I need the or way of thinking. So what came out of the ideas of Bohr and Heisenberg and Dirac and people in the 20s and 30s was, well, there must be some some new bit of physics, some way in which that Schrödinger equation we saw earlier isn't the whole story. So suddenly the wave function stops being peaked here and here, and it jumps, it collapses.
So let's see a quick picture of that collapse. So if we have a probability wave here, and this is the and description in your language. It could be in these variety of different locations. And I now undertake a measurement, and I take that measurement, and it collapses to the or way. It's only at one of those
Suddenly
particular
it's here,
locations.
and the rest of the wave function is gone.
And now if I turn away, and I'm stopped measuring, it melts back into the probabilistic description, and we're back to a language that feels quite unfamiliar, where the particle is in some sense at all of these locations simultaneously. Now, the issue that you raised is you said, look, we're going to have some other math to make this happen. So first, if we just use the Schrödinger equation, this beautiful equation that was written down, would that be enough to cause a wave to undergo that kind of transformation? Nice and spread out, and now collapses to one location where the particle is found. Can the Schrödinger equation do that for us?
No.
Birgitta? No. 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 That means no, right? It means yes. Okay. So like I said, Gerard has distinct views which are spectacularly interesting. We're going to come to those in just a moment. But let's now follow the history of the subject, where we're going to just follow our nose and we look at the equation that we have, and it doesn't do it. So what then do we do to get out of this impasse? And to make this impasse even a little bit more compelling, I'm going to take you through one version of this story that I hope will make the conundrum as sharp as it can be, and then we'll try to resolve it. So I'm going to take you through a little example over here where we have, say, a particle somewhere in Manhattan. And let's imagine that the probability wave makes the particle location peak at the Belvedere Castle in Central Park, just randomly chosen. What that would mean is if somehow I had some measuring device that could work out where the particle is experimentally, observationally, indeed, it would reveal that the particle is at that location. The wave is sharply peaked at that spot, and therefore all the probability is focused right there. That's quite a straightforward situation. Imagine we do the experiment again, and the probability wave has a different footprint. Let's say it's way down there at Union Square. If you follow the same experimental measurement procedure and you go about figuring out through your observation where the particle is, you find, indeed, there it is, Union Square. The conundrum is the issue that David was speaking to, where we now have a situation where we don't have one peak, but two. Now, it's sort of like the particle is at the Belvedere Castle and in Union Square. And that's puzzling, because if you go about looking at the observation, what do you think will happen here? Well, the naive thing is your detector kind of doesn't know what to do. It's sort of caught between the particle is at Belvedere Castle and it's at Union Square. But the thing is, nobody has ever found a detector, well, I should say nobody who is sober has ever found a detector that does this, right? This is not what we experience in the real world. So this is the issue that we have to sort out, because that naive picture is not borne out by experience. And I think many people here and many people in the community have thought about this. You, in particular, David, believe that you have the solution. It has a long historical lineage, but why don't you tell us a little bit about the approach that you think resolves this?
Okay. So start by reminding ourselves, what's the problem with just saying that the wave function suddenly jumps to being in Belvedere or Union Square? And the problem is really just that we have to modify the equations of physics at every level to handle that. And change,
because the Schrödinger equation just does not let that happen.
And to put it mildly, we've got quite a lot of evidence for that structure of physics. And for a whole bunch of reasons, actually trying to change the physics to make that sudden collapse of the wave function physical, and not just, as Gerard was putting it, not just a sort of fuzzy talk, is a really, really difficult technical problem. But you could say, look, we have to do that because, like Brian was saying, it doesn't seem we ever see a particle here and here at the same time. And I think Brian's joke is about right as to what our intuition is about what it would be like to see a particle here and here at the same time. It would be like being really drunk, like seeing double. But here's the thing. If you want to work out what some physical process would be like, and my looking at a particle is just one more physical process, turns out intuition is not a very good way to predict what happens. So how do we ask, what would it really be like to see a particle that's here and here at the same time? Well, what does the physics say? I'm just one more measurement device. And the physics says something like this. If I saw the particle here, I'd go into a state that you might call a seeing the particle here state. If I look at the particle there, then I go into what you call a seeing the particle there state. If it's in both states at the same time, then I go into both states at the same time. So being a little loose for the minute, then I'm now in the state seeing the particle here and seeing the particle there. And if I tell Brian where the particle is, because I'm sure he's fascinated, Brian's now in the David says it's here and David says it's there. And the whole audience who have to listen to me say this, you're now all in the it's here and it's there state at the same time. And the reality is that even if I don't tell you this, uncontrollable effects spread outward. And so before you know it, the whole planet, the whole solar system is in a particle was seen here and particle was seen here at the same time state. And those two states don't interact with each other. They're way too complicated to do the sorts of interference experiments we were doing with the two-slit. You can't do a two-slit experiment on the whole planet. And so for all intents and purposes, what the quantum theory is now describing is two sets of goings-on, each of which looks for all the world like the particle being in a definite place. And that's where the terminology of this way of thinking about quantum mechanics comes about, the many worlds theory. It was Hugh Everett who said, look, if you just take quantum mechanics seriously, you're led to this crazy-sounding idea of there being many parallel goings-on at the same time every time you make a quantum measurement. But the thing I want to stress here is it's not that we say quantum mechanics is weird, but let's bring in an even weirder idea out of the realm of science fiction to make it even stranger. It's what Everett was saying, and what people who've pushed his idea since then have been trying to make precise, is the idea that the quantum theory itself, that Schrödinger equation itself, when you take it really seriously, tells you that not at the fundamental level, not at the level of the microscopic physics, but at the level that we see around us in the everyday, then the physics is describing many goings-on at the same time. The quantum probability wave carries on being an and wave all the way up.
So you're talking about many universes.
Many universes.
So this is where this idea of parallel universes or many worlds come from. So in the example that we were looking at, there would be, say, if you were undertaking this measurement, there'd be you seeing the particle at Belvedere, you seeing it at Union Square, and as you said, once you articulate that, we're all hearing it, and we're all going along with you in one universe and another.
Exactly.
So that's one approach to trying to disambiguate a situation in which the quantum mechanics has many possibilities. You're saying, no, it's not just that one of them happens. They all happen. They all just happen to happen in distinct universes.
Right. And weirdly, that's a conservative idea.
Mathematically conservative. Yeah. And that's actually a vital point. And this is an idea that's hard to communicate to a general audience. I'm sure many of you are technically trained, but those who aren't, if you stare at the equations of quantum mechanics and just take them at face value, this seems to be where the math takes you. But does that convince? So are you guys convinced? Birgitta, you...
There are alternative perspectives.
But what about, why don't you like this one?
I like it. I think it's fascinating. I think it's wonderful. But let's bring in some information. So how much information are we going to keep? So this many worlds hypothesis would say that we're keeping every single piece of information.
Yes.
But if we have a measuring device, and then the measuring device is interacting with an environment, and the environment of outside is also playing a role. It's also affecting the measuring device. And of these many options, measurements that can be recorded by the measuring device, if the environment which is interacting with that measuring device is interacting with the measuring device and produces many more outcomes, and yet then we throw, in producing much more information, but then we throw all of that information of the environment away, then we're left with something which reduces to just a one one of these options.
So you're talking technical language of what's called decoherence.
Yes, I'm introducing this technical term that the coherence of the wave function, the preservation of these.
So your belief is that if we don't focus just on the simple particle itself, but take into account how it talks to and interacts with the full environment, you feel that that's enough to solve the conundrum?
Well, there's also mathematics to justify this. So this is another perspective. I'm not saying we don't know which is the one, but this is a very strong argument for saying why we don't actually experience many, many universes at once.
What's your view on the many?
Yeah, I mean, I think it's what you were describing. I mean, it's basically just going all in on the Schrödinger equation, saying, okay, we've got this beautiful equation. It applies to the atomic world. Let's take it seriously, and just if we believe in it, then I mean, you not only kind of understand through the mathematics there that at the local level you would effectively get something like collapse if you look at just a part of the description of the system, but then the only thing is that in the end it's a little bit disturbing philosophically that there's maybe a part of the wave describing the universe where I'm a football player, or then the question of, well, what is our experience in that picture of many worlds? Is there some way to understand why it is that we're just experiencing one thing? And
so Gerard, how about now? I know that you're going to take us somewhere else now.
No. When you asked me about this question about the wave function, you were nodding. I was supposed to not know, and I nodded yes. And I got you off track for a moment. And the point is this, that quantum mechanics today is the best we have to do the calculation. But the best we have doesn't mean that the calculation is extremely accurately correct. So according to the equations, we get these many worlds. I agree with that statement, but I don't agree with the statement that quantum mechanics is correct, and so we have to accept all these other universes for being real. No, the calculation is incomplete. There is much more going on that you didn't take into account. And then again, you can mention the environment, other things that you forgot. So we are so used in physics that unimportant secondary phenomena can be forgotten. We just leave them out, and then we take the calculation for granted. But if you do that, you don't get for certain which universe you are in. You get a superposition of different universes. It doesn't mean that the real outcome, that what's really happening is that the universe splits into a superposition of different universes. It means our calculation is inaccurate, and it could be done better. And that doesn't mean that our theory is wrong, but that we made simplifications. We made lots of simplifications. Instead of describing the real world, we split up the real world in what I call templates. All the particles you talk about are not real particles, they are just mathematical abstractions of a real particle. We use that because it's the best we can do, which is perfect. It's by far the best we can do. So in practice, that is just fine. But you just have to be careful in interpreting your result. The result does not mean that the universe splits in many other universes. The result means, yes, this answer is the best answer you could get. Now look at the amplitude of these universes that you get out. The one with the biggest amplitude is most likely the rightest answer. But all the other answers could be correct or could be wrong if we add more details, which we are unable to do. Because those details today, and perhaps also tomorrow, we will also will be unable to do it exactly, precisely, correctly. So we have to do with what we've got today. And what we've got today is an incomplete theory. We should know better, but unfortunately, we are not given the information that we need to do a more precise calculation. That precise calculation will show wave functions that do not peak at different points at the same time, like you had in Manhattan, that this address or that address, and we are in a superposition. No, in the real world, we are never in a superposition, because the real world takes every single phenomenon into account, and you cannot ignore what happens in the environment and so on. If you ignore that, then you get all these crazy superposition phenomena. If you would do the calculation with infinite precision, which nobody can do, if you calculate everything that happens in this room and way beyond and take everything into account, you would find a wave function which doesn't do that. You would find one which peaks only at the right answer and gives a 0 at the wrong answer.
Now this view...
But the theory is so unstable that the most minute incorrectness in your calculation gives you these phony signals that say maybe the universe went this, maybe the universe did that, maybe it did that. Only if you do it precisely correctly, then you get only one answer.
Yeah.
But
now that resonates obviously with an idea that goes all the way back to Einstein, that quantum mechanics is incomplete.
I think Einstein would agree with such.
Yeah, I think that he would too.
Maybe it's not true. Maybe you have your own ideas. But anyway, it is. To me, it sounds like an Einsteinian attitude that no, nature is absolute. God doesn't gamble. The gamble is in our calculation because we can't do any better.
So let's take a step back and see why Einstein came to this conclusion that quantum mechanics is incomplete, which takes us to the next strangeness of quantum mechanics, which is something called quantum entanglement. So this is an idea that has a long history in physics. I would not call entanglement, which we're about to talk about, one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So here's again one of the founding pioneers of the theory who thought about this notion that we're about to describe as the key element that distinguishes it from our intuition and our classical way of thinking. And as we'll see, it quickly, in the hands of Einstein, takes us to a viewpoint that aligns really with what Gerard was saying. And that comes most forcefully in a paper from 1935, a date that's good to keep in mind because we're going to come back to it in just a little bit, where these folks write a paper, Einstein, Podolsky, and Rosen, and we can just, this is actually a New York Times article on it, and you see that they call the theory not complete, much as Gerard was describing. And it's good to get a feel for why it is that they came to this conclusion. And it involves this idea of entanglement, and I'd like us to walk through that, just some of the key steps. And it's good to do it in the context of an example. It's not the example that Einstein and his colleagues actually use, but it's an example having to do with a quality of particles called spin. So just to set it up, and then I'll let the panelists take it from there. When we talk about a particle, say like an electron, it turns out that it has a characteristic called spin. You can think of it almost like a top that's spinning around. And roughly speaking, using classical language, just to get a feel for it, if the spin, say, is counterclockwise, you say it's spinning up. If it's clockwise, you say it's spinning down. And weirdly, a particle can be in a mixture of being both up and down, using your language of the and. And only when you measure the particle do you find that it snaps out of that mixture and is at, in the case of the particle Manhattan, it was either at one location or another. Here it's one spin or another. It's spinning down or up, but it's definite after you do the measurement. You never find it in between. Again, you can do a second measurement and say it snaps out of this fuzzy haze and it's spinning up. And that's a quality of a single particle that's well known in quantum physics. But entanglement arises when you don't have one particle, but rather when you have two of them. And here's the weirdness that happens. If you do a measurement in this situation, even though each particle is 50% up or 50% down, you'd think they're completely independent, but you can set things up in such a way that when you do a measurement, it's always the case that if the one on the left is up, the one on the right is down. They never are both up or both down. And we can go back to this story again, do another measurement, and they can be as far apart as you want, and you measure it, and you find, say, that the left one is down and the right one is up. So they're kind of locked together by a quantum connection, quantum entanglement, which just graphically we're representing by this little yellow line over here. Now, Gerard was talking about incompleteness of quantum mechanics. What was Einstein's view of what was going on here? Well, Einstein's view was that really what's going on here is if you have particles that the math says are both spinning up and spinning down at the same time. If you could look deeper to the deeper structure that Gerard was referencing, you'd find that these particles always have a definite spin. They're not actually going up and down. That's just mathematics. They actually have a definite spin, and therefore if you measure them and find that one is up and the other is down, they were already like that. It's not as though there was some long distance connection or communication going on. And this is what's known as quantum entanglement. And when I describe this to a general audience, people often get the phenomenon. Yeah, you measure it here, it's down, you measure it there, it's up. But then they always come back to me and say, but what's really going on? You know, like, but just explain to me. I say, I just did explain to you what's going on. That's all there is. No. They say, please tell me, like, how could this be? So how should we interpret this result? So Einstein says the way you interpret it is, it was like this the whole time, nothing surprising. But then we try to do experiments to see if that's the case, and what happens. So there's a famous person that comes into the story who... John Bell. And so what does Bell do for us?
I mean, basically, to put it simply, he finds that any kind of simplistic Einstein-like description where the thing had the definite configuration before we did that measurement, it can't explain the results. So you just
so when you say the results, you're talking about observational results.
That's right.
So so he writes this famous paper. What year is this? 1964? I think this.
Something like that, yeah.
I think it's like 1964. He writes this famous paper where he surprisingly is able to get at an experimental consequence of an Einsteinian view, that things are definitely up or down before you look. It's just the mathematics that's giving this weird superposition quality. And then people go out and ultimately, starting, say, with John Clauser in this must be the 70s, then into 80s with Alain Aspect, they carry out the measurement, and they find, as Mark was saying, that the Einsteinian picture doesn't describe the actual data. So if Einstein were here, I think you'd have to conclude not necessarily that quantum mechanics is complete, but the chink in the armor that he thought he found isn't actually correct. So Gerard, what's your because you're coming at it from an Einsteinian view. How do you deal with, say, this very experiment?
May I just add one point?
Please.
First? You can think of a classical experiment as very simple, but not strange at all. Think I take two marbles in a black box.
Sure.
One marble is red, the other one is green. Now, I shake the marbles as much as I want. I put blindfoldedly, I put one marble in one box, another marble in another box, and now I bring these boxes light years away from each other. As soon as somebody who sits, or say let's one on Earth and one on Mars, so somebody on Earth opens his box, and at the same time, the guy on Mars opens his box. Before they opened the box, they didn't know what kind of marble they had in the box. Was it the red one or was it the green one? You don't know. But as soon as the one on Earth opens his box and sees I have the red marble, instantly the guy in Mars knows that he has the green marble. That information went much faster than light. But you also know all this is nonsense, because they knew it in advance. Right, that I had one red and one green marble. So what's the big issue? No problem, right? So the Bell experiment is fundamentally different from this situation, in the sense that...
Yeah, so what you described, you described sort of the Einsteinian picture. Einstein would say, don't get worked about entanglement, it's just like having a green marble or red
marble. The Einsteinian picture would work perfectly well for the box with the red marble and the green marble. No sweat, no difficulty. We understand that situation. No miracle at all. But for the Bell light experiment with the spinning particle, you are using the fact that the particle is a quantum spinning particle. And a spinning particle is something very, very strange, which is it can either spin up or spin down. But then someone asks, what about spinning sideways? Why not rotate the particle 45 degrees or 90 degrees? And then say, yes, but that's a quantum superposition. But now if the one person on Earth looks at the particle in spinning up, the one on Mars sees it spinning down, but then when the person on Earth sees a particle spinning sideways, the guy on Mars sees the particle spinning sizes in the other direction.
Right.
And sees it either spinning up or spinning down, we still don't know.
In the sideways direction.
But when they both look in the sideways direction, they again see the spin opposite in opposite. And that is the miracle.
Yep.
That is a thing which is very, very difficult to understand classically. I maintain, but this is my private opinion, that you can explain it.
How?
But it is
because this is where Einstein
because they both
failed.
had the same origin. They both came eventually from an atom emitting two spinning objects, or two photons, or two electrons, or something like that, which were entangled. And so the entanglement can be explained in terms of correlations, so that the initial state was not that the particle could be doing just anything. No, there are correlations all over the place. This is very, very difficult to explain, and I wouldn't even dare to try to go into my argument in any depth. But the answer lies in correlations.
Do you think there is a way out of this impasse?
I think there's a way out, but it's extremely non-trivial, and if you don't do it quite right, you enter mystified, that end up being mystified by the situation.
Yeah.
It is actually also extremely hard to make a model that works, that gives this strange-looking phenomenon.
Right.
So, so yes, we have a problem, but no, I think the problem has an answer. But the answer is very difficult, and you have to work very hard to make it all hang together properly.
So that'll be in the footnotes to tonight's program. You'll receive it in your email. So David, your view on entanglement, is there a mystery here, or
there's a kind of mystery, and it kind of links to our earlier mysteries. I mean, look at it this way. My probability wave for the two spinning particles, you can kind of describe as something like half is this down up and half is this up down. And again, we can ask this: well, do I want to think about it as an and or an or? Do I want to say, well, it's this or it's this, or do I somehow have to say it's this and it's this? Now, if it's this or this, that's Gerard's case. That's not mysterious at all.
Right.
And that's exactly what Einstein and Podolsky and Rose and Hooft was the case. But what Bell's results show us is that the this or this reading of entanglement, just like in some ways the this slit or this slit reading of the two-slit experiment, would lead to experimental predictions that don't pan out. We can't, at least straightforwardly, we can't make sense of the experiments without seeing the entangled system as being this and this. And now we're right back to the mystery, because understanding how it can be this and this, which seems to imply some sort of deep connection between the two systems, where somehow saying everything there is about this side and everything there is about this side separately doesn't tell you everything.
Right.
That weird reading seems compulsory.
Right. So Birgitta, your view on this, should we fret about entanglement? Is it?
I think Gerard raised a very important point, is that when one talks about entanglement, one should not forget to say how the particles got entangled.
Yes.
And they get entangled through an interaction. And I think to most physicists, entanglement is not so mysterious if we think about it in those terms, because so even in just atomic or molecular terms, so take the two electrons in the helium atom. In the ground state, the helium atom is, if we were to separate the two electrons, we know we can't do that because they're sitting on top of each other, but were you to be able to take those two electrons and pull them apart, they would be in a perfectly entangled pair. But we know how they got there because they had an interaction that put them into a particular electronic state. And so if you just randomly put two particles together, they would not be entangled necessarily.
Yeah, to my mind, though, the very fact that I don't care how you set it up, the fact that you can set it up still makes me, in Niels Bohr's language, dizzy. Yeah. But yes, I agree. That does mitigate it to some extent, but still it's so far outside of common experience that it's still hard to grasp. But for this purposes, let's assume entanglement is real, because now we want to move on to think about how it manifests itself in some unusual places, like in the vicinity of a black hole. So that's the next thing that we're going to turn to. And for that extent, let's move on to the next section, quantum mechanics and black holes. And we'll also begin with a little clip.
Lisa, do you have a stray dog down there?
It's a lot worse than a stray dog.
2 stray dogs?
It's a black
That was gonna be my next guess.
Are you sure your next guess wasn't 3 stray dogs?
Baby.
All right, so black holes. I think most people here are quite familiar with what they are, but just again to get us on the same page, Mark, just describe what is a black hole?
Yeah, so that comes out of Einstein's picture of gravity and how the space that we live in is not a sort of passive background, but it's dynamical. It can warp and bend, and it does that kind of in response to the mass and the energy that's in the universe. And the black hole is the situation where you take that to the extreme. You have so much matter. Could be a gigantic star at the end of its life when it's burned up its fuel, and then it starts to collapse. And as it's getting denser and denser, it's warping the space more and more through Einstein's picture. And at some point, you get the space or the space-time that's warped so much that you get the thing we call a horizon. You get the point of no return, where if you go past that, you can't get out, you can't send signals out, light can't get out, and that's our basic notion of the black hole.
Now, there are many puzzles about black hole, and some of them are right at the forefront of research. There's one in particular that I want to focus on, as it will bring together these ideas of entanglement and ultimately the structure of space-time, which is where we'll get to in the next chapter, which is simply this. If something falls into a black hole, what happens to the information that it contained, right? So to just be concrete, imagine I was to take out my wallet and throw it into a black hole. My wallet has all sorts of information, credit card information. Oh, there it is. They took it out of my pocket. They throw it into the black hole. It crosses over the horizon, the edge that Mark was referring to. And at least in the non-quantum, in the classical description, it's just gone, right? And you can think that the information is sort of maybe still there. It's just on the other side. We can't get at it unless we go in. But if we do that, there are consequences. We can't come back out with the information. So that's sort of the classical story. This becomes a really big puzzle and a bigger puzzle when we include quantum mechanics into the story, because of a result that was due to a couple of very insightful physicists, one who you may not have heard of, one who you will have heard of. So back in the 70s, Jacob Bekenstein, and also this fella over here, Stephen Hawking, they began to apply quantum ideas to black holes and found a surprising result, which is that black holes are actually not completely black. So anyone just to jump in and what is it that means? Or Mark, go ahead.
Yeah, so Hawking found when you start to apply quantum mechanics to the physics in the vicinity of a black hole, that there are quantum effects that lead to the black hole seeming to emit particles out of it, as if
I think we have a little picture that can help.
This is sort of a quantum effect where you have something happening right at the horizon of the black hole, where what we would call virtual particle and an antiparticle.
Say particle is red, antiparticle is blue.
Antiparticle is blue. So this can happen in quantum mechanics, but because of the black hole horizon, the particles end up going out, and so what it looks like. And their
partners fell in, they went out.
We don't see those partners, and so
which
you're
would
losing
mean from far away. If we look at this situation.
That's right. So there we go. So the black hole looks like it's emitting stuff, and it's actually losing some of its mass. So you see it's getting smaller. Hawking did a detailed calculation to show that it's behaving like an object that's getting hotter and hotter and hotter, and sort of we call it evaporating more and more quickly, and ultimately disappearing. So all of this information that might have been in the black hole, it's now this heat, this thermal radiation going out into space.
And all of this is happening, if I understand. So you got the edge of the black hole, you got this quantum process right at the edge that we're familiar with. Particle, antiparticle sort of pops out of empty space. The difference is now with the black hole there, it can kind of pull on one member of the pair, it gets sucked in, the other just rushes out, and that gives rise to radiation flying outward. And that's what makes this puzzle sharp, because if the wallet goes into the black hole, and then you have this radiation coming out, ultimately, and perhaps the black hole even disappears through this. Everything that went in has come out, but if the radiation itself doesn't have an imprint of the wallet, doesn't somehow embody the information would be lost.
And Hawking's calculation showed that it should not matter what formed the black hole. You get exactly the same radiation coming out.
So whether it's my wallet or whether it's a refrigerator, chicken soup, it all would sort of come out the same. The information is lost. Now this disturbed Gerard
Very
deeply.
much so.
Yes.
Very much so. But the statement you just made was only about the average Hawking particle. The Hawking particles form what we call a thermal spectrum, which means that they come out in a completely, fundamentally chaotic way. But it doesn't mean that they don't know in what way they come out. Again, it's quantum mechanics, but again, there is a theory underlying quantum mechanics which is more precise and which should provide the missing information. And yes, there was missing information, and yes, your wallet does leave an imprint on the radiation coming out.
So can we show?
Because your wallet, yes, if you want to have a moment, your wallet carries a gravitational field. Even though it's very light compared to a planet or a star, it does have gravity. That gravity is sufficient to leave a very minute imprint on the outgoing particles.
So we sort of see that imprint here of my wallet on the edge of the black hole.
The effect of this is that the information gets stuck on the horizon of a black hole.
Can we just show that one again?
Ready to come out again in the form of the Hawking particles.
Right.
And this, in principle, you can compute, and you find that the culprit is the gravitational field of your wallet. That many people forget to take into account. And then you get a tremendous problem. They don't understand how can it be that all those dollars in and credit cards in your wallet, that information gets out. Well, a normal person will never be able to identify, to decompose Hawking radiation and get back to your wallet.
So they won't be able to do this.
It's a beta shredder you'll never find anywhere.
Right.
But even the shredder still contains the information.
Right. So people won't actually be able to do this, reconstruct my
No,
wallet, but in
practice,
principle, just like with the shredder, in principle they would be able to do that. So this is an idea that you developed also with Lenny Susskind, which gives rise to what we call the holographic principle, the holographic description. Again, because if information is stored on a thin surface at the edge of the black hole, it sort of brings to mind a hologram, which is a thin piece of plastic which has etchings on it. When you illuminate it correctly, it yields a three-dimensional entity. Here, you've got information on this thin two-dimensional surface, which is able to reconstruct the object that went in, and that's why this word holography is used. So this is sort of a deep insight which has been generalized. People, Gerard and Lenny and others, think that perhaps the right way of thinking about the universe, any environment, even right here on Earth, there's a description where data exists on a thin two-dimensional bounding surface, which would make us the holographic projections, using this language, of this information that exists on a thin surface that you wouldn't think would even have the capacity to store enough information to make it adequate to describe all the comings and goings in this three-dimensional realm. Yes, Dave?
Yeah, I mean, just want to sort of pin down for a moment, like, why should we have cared in the first place that the information was lost? But by assuming the information is not being lost, we've made our way to remarkable new ideas in physics. And I think there's sometimes a temptation to think, well, yeah, maybe that's the wrong lesson. Maybe what we should learn is, well, information disappears sometimes, deal with it. And I think
Which is what Hawking
himself
said.
thought, exactly. And
Right.
there's still a minority of people in physics who take that line.
Yeah.
And I think the deeper reason to think why...
But Hawking doesn't take that line
Hawking's
in
changed
it.
his mind,
Yeah,
right.
good.
And I think the deeper reason to see why information being lost is such a problem goes back to where we started, the idea that black holes are hot. Now, everything else in the universe we know that's hot has a story to tell about why it's hot that basically says it can be in zillions and zillions and zillions of different states, and by statistically averaging over all those states, we get out the hot behavior. That's how thermodynamics is grounded in microscopic physics for every other hot thing in the universe. If information is lost forever in black holes, then black holes are hot for a fundamentally different reason than why everything else in the universe is hot.
Yeah.
And this whole story about holography and about information being preserved is basically a bet, and it seems to me a very well-motivated bet, on the idea that black holes are hot for the same reason everything else is hot.
Right, right. So again, one way of saying that is when a black hole is radiating, It's radiating because, in some sense, stuff is burning near the edge, even though all the matter that fell in is compressed at the center. And that's unfamiliar, because when a star burns, it's burning at its surface. So the stuff responsible, the fuel, is burning right where the radiation is emitted. But with a black hole, all of the fuel, all the mass is here, whereas the radiation is coming out over here. And that distinction might suggest that it's a different kind of burning, but you're absolutely right. If we want all the usual ideas of physics to work, it better be the same kind of burning, and that's what the approach of holography provides for us. And what I'd like to do now is, if we can jump actually to the next chapter, just because time is a little bit short, I want to take this idea of entanglement and Mark.
Yeah, let me just introduce that a little bit. I mean,
Yep.
one of the things, Hawking did his calculation in an approximation where he didn't have a theory that actually combined gravity and quantum mechanics. He was using bits of quantum mechanics and Einstein's theory and coming up with this result that you lose information. And that, if that were true, it would say that gravity and quantum mechanics are incompatible. You have to change quantum mechanics somehow, but in quantum mechanics, you never lose information. And so this is why this holographic insight of Gerard and others is so important. It sort of has given us a way of avoiding Hawking's conclusions, and Hawking has accepted that. And so this way, there's now, it's been for the past 20 years, we've got a way of kind of doing quantum gravity, of combining gravity and quantum mechanics, and it uses this holographic idea in a completely essential way. And it was like that picture of the Earth with the data around it. It's kind of like saying that our reality that we experience, this gravitational universe that we're in, there's kind of an underlying reality which you can think of as those bits, those ones and zeros on the surface surrounding us, and that's what Brian was referring to as the hologram. So somehow, if you want to understand the quantum mechanics of a system with, say, black holes and gravity, what you really want to do is understand the quantum mechanics of that hologram, and not kind of directly try to do the calculations like Hawking did of the black hole.
So it's a very powerful, come to half a second just to summarize that point. It's a very powerful dictionary in some sense. You now have two ways of describing a given physical system. You can describe it sort of in the conventional way that we've always thought about it, as a three-dimensional world that has comings and goings, or you have an alternative language if you want to make use of it, which is the physics that takes place on this thin bounding surface. And sometimes that latter description gives you insights that are very difficult to obtain from the traditional description. And we're going to come to a version of that in just a moment. But yeah, Gerard.
Yeah, I think that you can make the picture a little bit more clear perhaps by realizing that whenever you throw something into the black hole, when you look at it from the outside, you'll never see it actually pass through the horizon.
Yep.
It hangs around at the horizon. So it shouldn't be too surprising that that information also hangs around at the horizon.
Yeah, so can I just flesh it out for half a second?
Yes.
So what Gerard is saying is, if you look at how a black hole affects the passage of time, you find that as a clock gets closer and closer to the edge of a black hole, the clock ticks off time ever more slowly. So if you're watching this from very far away, the object is starting to go in slow motion as it goes toward the edge of the black hole. It doesn't just immediately go over the edge. In fact, it goes so slow that it would take an infinite amount of time from your perspective for it to actually fall over the edge. So it hangs out there.
The outside observer would think the clock is standing still.
Standing still.
But actually, the clock is simply showing the time that the observer who goes with the clock sees that, oh, that's the time I'm going through the horizon.
Right.
But for the outside observer, that's the eternal time. It never changes anymore. The other observation one can make is it's a very elementary calculation to find out how can we put other kinds of information in such a box. Take a box with a certain radius, or let it be spherical for simplicity, and ask how much information can I put in a box no matter what I do. So take a gas, or take a liquid, or take a dictionary, throw anything in a box. When do I get the maximum amount of information? You can calculate that, and what you find is if you try to put more things in a box, that takes so much energy that those encyclopedia that you try to put in this box will automatically make a black hole. And what is the object that contains the most information you can ever imagine? It's the black hole. It always wins.
Right.
So the black hole is the maximum. There's no way, no matter what you put in the box with a given radius, to get more information in that box than what fits on the surface. And that's the holographic principle. Information is two-dimensional, not three-dimensional.
Right.
And that is very strange. That's why I call it holography. It is as if, we have a three-dimensional world, but you take a picture with the machinery of a holography. I don't know whether you know it. It's a camera which makes a picture, and if you look at the picture from different ends, it looks like reconstructing the three-dimensional object.
So
but it only exists on a two-dimensional
Did you
surface.
doubt this idea when you first...
This is in discussions with Lenny Susskind, the word holography came up.
Right, but I mean, were you certain that this was right when it popped out, or was this so strange that you were...
Well, no, it is very strange, but I said, well, this comes out of the calculation, must be true. But it's very, very counterintuitive.
Yeah.
It's like saying our reality is not as real as we think it is.
Yeah,
it's
right.
Like,
Which for most of us is pretty
so
odd.
the question is, what happened to the rest of the information, the three-dimensional information? Does it disappear? Does it get lost? This is a sort of mysterious aspect of our space-time.
So let's take this holographic idea and push it one step further, which, Mark,
yeah,
you have been
so if we take it seriously,
but before we get that, because there's one thing that we didn't discuss that would be useful, and it's right here, which is something else that happened in 1935. Which is the idea of wormholes. So if you can just take us through what a wormhole is, and then we can make
so the wormhole, if you set to solving Einstein's equations to figure out, well, what kind of geometries are possible for space-time, then there's a weird thing that comes out where it's like you have a black hole in an empty universe, and then there's this entirely separate universe with another black hole in it.
At the top and the bottom of this picture.
Yeah, that's the space. The flat part is the space in one universe, and then this is like a black hole. But you see it's connected down to the flat part, which is like the other universe.
Yep.
And there's this physical geometrical connection. So if one person jumped into one black hole and the other person jumped into the black hole at the bottom, they could potentially meet up inside that wormhole, before being annihilated by the
So it's sort of a tunnel connecting these two things.
That's right.
Are you volunteering?
I'll pass on that one.
So you may recall I said, remember the year 1935, that was at Einstein-Podolsky-Rosen, which was the entanglement that we've been discussing. This is also 1935, where it's Einstein and Rosen, so again, two of the three folks involved. And in Einstein's mind, I think it's pretty clear, and correct me if you think otherwise, I don't think he thought there was any connection between these two 1935 discoveries. Entanglement on the one hand, coming from quantum physics, wormholes coming from general relativity,
Absolutely.
a completely separate subject at the time. And some of the work that you and various of our other colleagues have been pursuing is suggesting that there's actually a deep connection between these ideas.
It's truly amazing.
So I think we'll sort of step through that now, if that works for you. So we have a little, you can sort of walk us through what we're having here.
So we're looking at some kind of universe. There's a black hole in this universe. And then what's on the outside is this hologram. This is like the actual mathematical description in our modern way of understanding. So this red around the outside has all of the information that is telling us what kind of geometry is in there.
So that's Gerard's hologram.
That's Gerard's hologram. On the outside, you've got that hologram in a particular kind of physical configuration. And that's coding for the fact that there's this black hole and maybe some stars in there in the space-time.
Yeah. And then if we go on and go to the second black hole in this story,
now we've got two separate black holes, and basically that's going to be encoded by some other information. So you change up the information, and now you've got two black holes.
Yep. And then if we add to this story a certain kind of entanglement, say, so
here, what we did was we turned that situation into one where you have a wormhole connecting behind the two black holes. And the remarkable thing is, in order to do that in the holographic description, in the outside description, what we actually, we have to do something fundamentally quantum mechanical. What we had to do is actually add in a whole bunch of entanglement between different parts of the hologram. And that was what achieved getting this
So just to summarize, because it's a deep and utterly stunning idea, you're saying that entanglement in the holographic description, the red description, is, in the interior description, nothing but a wormhole connecting two black holes.
That's right, which is just a sort of a classical thing that would have been covered by Einstein's kind of classical understanding of gravity. It's just a geometrical connection saying you could get from here to here. And that property is entirely, according to our current understanding, due to quantum entanglement between different parts of the hologram.
And moreover, if you find that you can actually generalize this, that it actually even holds without a black hole in the space. So take us from here.
Yeah, so this was, I guess, 2009. I was thinking about that. It seemed crazy, and then one of the things that you realize if you start reading about entanglement and about just our description in these theories of just empty space, is that even when you're describing empty space, you still have entanglement in the hologram, in the holographic description. There's lots of entanglement. And then you sort of ask yourself, well, wait, if that entanglement in the previous story was creating a connection between the two black holes, could all of this entanglement there in this picture, could that have something to do with the fact that the space is sort of connected up into one nice, smooth, empty
that space
universe?
Has threads in some sense. We call it the fabric of space. Is it somehow threaded in some manner?
Could that be related to this entanglement?
And then you were able to mathematically study that by mathematically cutting the entanglement lines on the outside.
Right, so it's what we'd call a thought experiment. You just sort of take your description of this, and you say, well, what happens if I cut those threads of entanglement? What happens if
we cut some of them,
take the left half of the hologram and the right half of the hologram, and I remove the entanglement between those two sides? There's an effect. You remove entanglement in the hologram, and then the space-time starts splitting up. And you can actually imagine even more than this, that you got a ball of clay, and you're pulling it apart, and it's getting further and further apart, and the middle is pinching off. And so you could keep doing that. You say, well, what would happen if I took away even more entanglement, and took away even more entanglement, and then in this model, now you've got your space and it's split into 4 pieces, and I've still got a little bit of entanglement, but I'm going to take that away. And what happens in this description is that the big, nice, empty universe that you thought you were describing just splits up into millions of tiny bits. And once you've got no more entanglement there in this description, you've got no more space-time at all. And so you get to, if this is all right, you get to this incredibly dramatic conclusion that maybe you've just understood what space actually is, and it's actually fundamentally quantum mechanical, that space is somehow a manifestation of quantum entanglement in the underlying hologram system.
There's this beautiful possibility that we may actually get insight into what holds space itself together, and it may be entanglement in this holographic description that's actually threading it all together, which is, I have to say, as a graduate student, you have dreams of the things that you might one day gain insight into. And certainly when I was a graduate student, the idea that we might somehow understand the fundamental structure of space itself, it was one of those unattainable dreams. And the work that you guys are doing is starting to reveal the possibility that we may actually get there. So I'm going to personally applaud right here, because that is just, an absolutely stunning insight, which puts together all of these ideas, the ideas of entanglement, the ideas of holography, all put together to gain these insights. So we're sort of out there in the depths of some pretty heady ideas. We're just going to spill over for a couple of minutes. I hope that's okay with you, because I just want to sort of pull us back a little bit to what quantum mechanics can actually do in the world around us that might actually affect the future of how we do various things. So, Birgitta, you work in the arena of quantum computing. What are the possibilities of actually harnessing these weird, wonderful ideas in a manner that could actually have an impact to say, computing power?
Well, so over the last 30 years, there's been a very rapid growth of the field of quantum information, which is really a marriage of information science and quantum mechanics. And this is still the quantum mechanics from the 1930s, 1940s. You don't even need relativistic effects for this. And what we've seen is, in the middle 1990s, there was a very dramatic publication of an algorithm for doing doing a calculation of factoring large numbers. And this was an algorithm due to Peter Shor, and this algorithm showed could be run many, many orders of magnitude faster if you had a computer that was built on the principles of quantum mechanics, using superposition states, using these wave functions, highly delocalized wave functions over many bits, and principles of entanglement, and then having, however, to maintain the very delicate quantum nature of the system and not allowing interaction with the environment to happen. But if you do this, and then at the end, after many procedures, quantum procedures, you would construct a very carefully designed measurement, and ideally you'd want one measurement at the end, and it would be the right measurement that would give you the answer to your calculation.
And are we going to reach this?
Yes, this was very important because factoring large numbers lies at the heart of most of our encryption schemes, encryption of your credit cards today, airline tickets, anything that you think of. And so from that moment on, in a sense, that sort of set the race to build such a quantum computer. And there's been a lot of advances experimentally then over the last 20 years. And we're now at the point where we have functioning devices with 9 or 10 quantum bits, the quantum analog of a classical bit. And in the quantum bit, so as we saw, there's examples of the spinning electrons. So a classical bit will either be in a state 0 or 1, our digital universe, which we saw in outer space just now. But a quantum bit can be in a superposition. It can be any arbitrary superposition of 0 and 1, which means it will be both 1 or 0, and at the same time 1 and 0. So it was carrying this mystery along with us. And so we now have devices that are functioning with about 10 of these.
You say 10?
10?
Yeah.
10. No. 9 actually is the canonical number right now.
Right, yeah.
But people are working furiously now to build up to about 50, 60, and within a few years we should have somewhere close to 100. And then once we get close to about 100, that's a critical number, because at that point one starts to have real technical challenges in maintaining the quantum nature of the states of these machines. And that brings in these issues of the environment, the decoherence, and also very, very delicate control. And as Gerard mentioned, then you really have to know many, 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 many variables to control every one of those variables. And that's a really big, both physics and engineering problem, which is just starting to be addressed now. And then after that, I think it's impossible to predict how long it would take after that, if at all possible, to go up to about 1,000 or so. And 1,000 is about the number where one would really have a machine which would do things that couldn't be computed in the lifetime of the universe on a classical machine.
Incredibly exciting.
So that would be the real change for information processing.
Amazing. So we're just about out of time, but I wanted to end on even bringing this even further down to Earth, because you sort of soared out to the cosmos, black holes, wormholes, entanglement. There's a wonderful demonstration in which these quantum mechanical ideas does something that I find eye-popping no matter how many times I've seen it. Maybe some of you have seen it before. We have our fingers crossed. Omalon, can you come out one more time with our with quantum levitation, if you would, which is a stunning demonstration of, again, some of the strange ways in which quantum mechanics allows the world to work in ways that, again, a classical intuition would not expect. And Omalon does this freehand. I'm going to stand back. And you want me to actually touch this? Well, I'm going to wear a glove. He only wears it to look like he's being responsible. I see him do this with the bare hand all the time. You know, that's just crazy. All right, that's like 77 degrees or something, you know, Kelvin, which is cold. Okay, so let's just go right to the disk, if you would. And if you just put that there, and then I'm going to give this a little bit of a push around. Can you see that up on the, can you get a shot of that? This is actually just hovering. Yeah. And I give it a little bit more of a push. And what's happening here, if you bring up the final slide that we have here, it's called quantum locking. It was a wonderful application of quantum ideas that originated with some Israeli physicists who demonstrated this once before. You've got magnetic lines that are penetrating this superconducting disk. It's cold, that allows it to be a superconductor. And the threads of these magnetic lines are able to sometimes pin this object along this track. The track has a uniform magnetic field, and as long as you keep it cold and superconducting, they will hold it in place. Here's another illustration of these ideas. Look at that. Can you get a close-up of that shot right there? Can you bring that up on the screen? There you go. So you see that's just hovering right there, and there's nothing in between there. And can we actually, can we flip this over and show how that goes? Yeah, so we can take this guy. And do you want, okay. And do you want a glove? No, you just want to do it by hand there. Yeah, okay, more fun that way, he says. Okay, yeah. Wow, that's insane. Okay, now, can you get a shot of that underneath there? It is now hovering underneath, which is a fairly stunning and, yes, right down to earth demonstration of quantum mechanics. So, Oman, thank you. So totally cool. Appreciate that. I want to thank the entire panel for what I hope was an interesting journey. David Wallace, Birgitta Whaley, Mark von Raamsdonk, and Gerard at Hooft. So thank you very much. Thank you.